0. Now, what happens after a long time? Well, let's think about it. You have a wall that's at an initial temperature that's lower than the ambient, and it's insulated on one side. So you have heat being convected into the wall, and it's sucking up this heat energy. Now the heat is falling from an ambient at a higher temperature into a material at a lower temperature. So what's the maximum temperature that that material can reach? It would be the ambient temperature. So in this case, this would be T infinity. That's the maximum temperature. Our temperature is going to be somewhere in between the ambient temperature and our initial temperature. Now, once it reaches an ambient temperature, the material does, what's going to happen to convective heat transfer? So you have Newton's law of cooling. The Q convection leaving the wall equals, let's say it's a flux, so we can normalize it by area. It's going to equal the heat transfer coefficient times T of the surface minus, or let's say in this case it's going into the wall, so this will be T infinity minus T at the surface. So you see H is constant. In order for us to have heat transfer into the wall, for us to continue to have that, T infinity has to still be greater than T surface. But if T surface equals T infinity, then our heat transfer stops. This goes to 0. So there were 2 points that were illustrated there. The first of which is that at infinite time after the initial, the temperature at any point x at infinity is going to equal T infinity. The second point will be illustrated when we look at drawing the heat flux. But let's draw 2 intermediate temperatures. So how is it going to move from T initial to T infinity? Well, we have convection happening here. This is x equals L, and this is x equals 0. Actually, let me, no, I'll leave it like that. So, when we first turn on convection, this temperature at the wall is going to jump up, and its presence, that boundary, is going to be felt at this really short time after 0. It's going to be felt just a little ways into the material, and it's going to decay, and then most of the material is still going to be at the initial temperature. So at this boundary, this slope is pretty steep. And this slope represents the heat conduction rate. And the reason it's very steep is because the difference between T infinity and T surface is its largest at the beginning. But as this material heats up, the difference between T infinity and T surface starts to decrease. This is at the boundary. However, the material also starts to get hotter and hotter. So near the boundary, the slope, the decrease in this temperature profile, or this slope, will be less. It will be more gradual. Yet, it's still going to do something like that. So steep slope here, not as steep here, because our heat rate at the boundary is changing because the surface temperature is changing. Ambient temperature is the same. So that delta T that drives convective heat transfer is decreasing. So our heat rate is decreasing. And the way we represent a decreasing heat rate at the boundary is by a decreasing slope. These slopes become flatter and flatter, and once it gets to the point where heat transfer is 0, then it's completely flat. So what does the So this is kind of covered up here, but next we want to draw the surface, the heat fluxes as a function of time at the two surfaces. So here, we're just illustrating again kind of what was just illustrated on the temperature plot. That let's say that this is x equal L again, and this is x equals 0. Then basically, the heat flux is going to start at some value that's high, and oops, well, I already have 0 defined. It's going to decay to 0. So we know at the insulated boundary it's 0. But as it creeps up, it becomes higher, like this. Now, this question was asking us to sketch the heat fluxes as a function of time at the two surfaces. So this would be Q as a function of time. However, this is really at one instance in time, like I said. So this would be maybe shortly after the heat flux, the surface convective heating is applied, we'd get something like this. But we just showed in the previous example that if time goes to infinity, eventually this heat flux will go down and everything is going to converge to a straight line where we won't have any heat transfer because there won't be any temperature differences in our system to drive the heat transfer. So lastly, we want to know the total energy transferred to the wall. So the wall, we have a wall that's insulated on one side, meaning heat can't come out on one side. Heat can only go in or come out on one side. That's the convective heating side. But we know that heat is only going in. So we have a wall that's at some uniform initial temperature, and we're dumping heat into it. So all the heat that's dumped into the system at the wall where convection is occurring, all of that heat is going to be built up in the system. So that's going to be the total energy that's transferred into the wall. So what we can do is, if we know that we have a heat rate, Q convection, coming into our wall, that equals heat transfer coefficient times the difference between the ambient temperature and the surface temperature. This is what we have. And this is in watts. This is why I always stress units. This is in watts. So how do we get this into joules? Because we want to know the total energy transfer. So, well, this total energy, let's say it's E total, is going to equal the integral of Q double prime convection from time equals 0 to infinity dt. So in this case, we know that our surface temperature, we already talked about this, and I'll draw it explicitly. Our surface temperature is a function of time. It's changing with time. And we can determine this function temperature with time from our heat equation, 1D transient heat equation that was the solution to part A. So we determine this surface temperature as a function of time. We would plug it into this relationship, and we would integrate this convection heat rate over time from 0 to infinity, and then it's going to tell us what the total energy transferred into the wall is in joules. So that's it for today, and on Thursday we'll go into more heat conduction. We're going to reduce the heat equation to the one-dimensional form, steady state, and no generation. And we're going to see a lot of the nice tricks we can apply to solve that problem and to work with it in many different ways. See you Thursday.